Okay, let's start our last talk for today. Last talk for our workshop. Yuancheng Xie from Peking University.
Okay. Thank you for the invitation, and I'm very happy to be here to give a talk. And the speaker of the last talk, it's my privilege to send the organizer, representative of other participants, especially those from Peking University. And also to declare like the success of this workshop up to now. Okay. Okay. So I will talk about the Toda lattice and Hessenberg varieties, which I will show you like other things are basically linear algebra, but it has some kind of interesting contents. So the talk will be in three parts. The first part I will talk about classical three-dimensional Toda lattice. And the second part, I will talk about the four Kostant-Toda lattice and its relation with lab variety. And in the third part, I will combine this together to explore the relation between Toda lattice and what's called the Hessenberg varieties. Okay. So the classical Toda lattice is a Hamiltonian system, which is described like a chain of particles, either on the line or on the circle. So and it's so we use the standard symplectic form to define the Hamiltonian system. I just need two things. One is like I need a symplectic form. The other one I need a Hamiltonian. And the Hamiltonian so there the kinetic part is always that, and the difference is the potential part. So the potential part tells us like the particles interact, and only nearest particle will interact with each other with exponential potential. Okay, so here is this Hamiltonian, and with that, with this standard symplectic form, I can write down equations for the position Q and also moment P, pk. Okay. So this equation was essentially written down in 1967, and by Toda. And already you already know that there's like a one silicon solution and also quasi-periodic solution of genus 1, but nothing else until in 1974. So Flashcon made this remarkable change of a variable. So you just make like a pk, give it another name ak, and but you make the exponential part bk. So what's the benefit of that? You can just write all the things in your matrix. You can write all the ai's, bi's in your matrix. And what I wrote here is actually belongs to Kostant in 1979. And the benefit of it, so then you can just put this into the Lux pair. Okay. So the Lux pair, the other part of the Lux equation is just the positive part, the upper triangular part of this L. So what's the benefit of this this form is that so all the AIs and BIs, and also here we have ones on the off diagonal. They have a very specific meaning in Lie algebras. So other ones are at the position of a positive root, okay, and other AIs are on their diagonal. That means you can just generalize the two Lie algebras with elements in Katan, and other BIs are that's the negative simple root, okay. So to do that, let me just introduce some very standard notation in Lie theory. So the first line is about Lie algebra. The second line is about the corresponding Lie groups. So G is their Lie algebra, same simple. H is Katan, and N plus minus is the nilpotent part, and H B plus minus it's for real. So that's basically the sum of H and N plus minus. Pi is the simple root system, and data plus minus, this is the Shapley system, root system. And omega I here is the fundamental weight, which I will use later. and H alpha I, X alpha, Y alpha, this is the Chadli system. So the second line is the corresponding Lie groups. I will not repeat. And the W here is the well group. Okay. So here then we can just basically define it on simple on other Lie algebras. For example, we can just my X alpha, the coefficient is 1. That's the ones on the upper off diagonal. And here AI, the coefficient of H alpha J. So it's given is AJ, the AJ is a diagonal, okay, and BJ is lower diagonal. So that's exactly what in type A. That's exactly what I wrote before, except like this AJ may be a little bit different. So I need to choose a basis. And if I write down the last pair, then and I expand it, I will find that. So this is looks very simple, but actually the equation here. The derivative of AJ is BJ, but the derivative of BJ is a sum of AJ, and the coefficient is a Latin matrix. And you know that the simple Lie algebra is uniquely up to isomorphism determined by its Latin matrix. So that means the simple system somehow already contained the information for Lie algebra. And actually we will show this is the case. And this Hamiltonian is also a very simple form. It's just a 1/2 of a trace of L squared. Okay. And actually, I mean, it's so I will show you immediately like this system is solvable. I will show you a way to solve this equation. So how do you do that? So to specify an ordinary differential equation, either in a linear or nonlinear, we need to specify some kind of initial condition, and that's my L0. Okay, at some point like t equals 0, I have my initial condition L0. So I do this. I do exponential t L0, and and then I do a factorization. So this is a Gauss factorization. And minus is a lower uniform matrix. So that's a lower matrix with ones on your diagonal. So it's invertible. So B plus is an upper triangular matrix, and the diagonal elements they have to be invertible. So not every matrix you can do this factorization. There's some kind of condition. I will say later. But as you can see that when t equals 0. It's identity matrix, you can always do this, okay? So since this factorization is an open condition, you can, when t is very small, you can always do this, okay? That's enough for our purpose, because when t is small enough, we have an interval that we can take derivatives. And then you can show that, so if you just use this B plus conjugate on this L naught, or use N minus t inverse conjugate on this L naught, you will get their solution. Because you can check two things. First, they have the same initial condition. Second, they satisfy the same differential equation, right? And then they have to be the same. So this is easy. But the problem is there's a problem like, okay, I give you every t, you have to do this factorization. And sometimes you don't know how to do this factorization. So that's the computationally, that's complicated. I will show you a way that you don't need to even do this factorization. You can write down their solution. So you can do it like this. Yeah, I choose so I really this a little fancy, but it's I will tell you what's in type A. It's actually very elementary. So here rho omega I is the fundamental weight. So rho omega J is the fundamental representation. And the V omega J is the representative space, right? And then we have a highest weight in this representation, that's V omega J. And then you just use this matrix, use this group element exponential TL naught, act on this V omega J. And on V, this capital V omega J, actually you can have like a Hermitian metric. And then you pair that with V omega J. Okay, so what does it mean in type A? It's quite simple. It just means like the V omega J, we know that it's just the wedge product of the CM. Okay. And you act on it on the right, so that does it That just means, okay, you take the columns of this first J columns. And the first V omega J tells you take the first J rows of this matrix. Okay, so what it says is in type A, what it says is how J here is just the principal minor, J's principal minor of this matrix exponential T L naught. Okay, that's the only thing that I need. So then a theorem of Kostant says that, okay, you just take the J's principal minor, you take a log of that, and then you take derivative with respect to T. That gives you the diagonal element. So you don't need to do the factorization anywhere, but this exponential, of course, that's you couldn't avoid. It's you see, like the simplest linear system, y prime equals y. You have to involve exponential, right? So simply it's a linear system. You have to use exponential. So exponential you couldn't avoid. But other than that, it's just like a linear system. Okay. And Bj, as we said before, Bj is just the derivative of Aj. So you just take another derivative and it's solved. It's done. And but now we want to understand. So geometrically, what we are doing. What we are doing is something like this. If we just look at the formula 3, we see that, you know, this is a B plus. So this is a B plus conjugate on L naught, okay? And L naught is what? L naught is a lower triangular matrix shifted by 1, 1, 1, 1, okay? But the lower triangular matrix is an element actually in B plus, it's dual. By killing form, I can identify B plus, it's a dual with B minus. And then I just shift. So L naught sits inside the space and shifted by this one. And as a fine space, they're the same. Okay. So this actually says like, so total lattice in some sense is just the co-adjoint orbit of B plus. Okay. And if we consider it like that, actually we know that B plus has a different realization of its dual has different realizations. If we just do QR factorization, then we can just realize B plus dual as the symmetric matrices. And that's actually, you know, Professor Shabin was supposed to talk about. And here we're talking about another realization of its dual. It's a lower triangular matrix shifted by these ones. And you are looking at that, and then it doesn't prohibit us to consider the general co-adjoint orbit. So we shouldn't just restrict to the you know, the tree diagonal matrices. We can just consider the whole co-adjoint orbit. So that means like I consider all the lower triangular matrices and shifted by ones. Okay, and I will just look at what will happen here. So I took up the same lattice matrices. Since this is the you know, the three diagonal ones were investigated by Kostant and were studied the full ones. So we call it a full Kostant lattice. So we could write down the same kind of differential equations. So so L is the lattice matrix, and we have this projection to you know, Borel parts, and then there we still have these nice things. So the first nice thing is that we can still do this factorization method. So it still works. You can just you know, go through line by line, and the argument still works. Okay. So that means we didn't lose the essential part that we want to keep. The essential part is we view LT as an element in the co-adjoint orbit of a B plus. And here we still have that. Okay, that's something good. But immediately we have a problem. It's you know, originally this is a physical problem, but now we want to use it to study geometry, to study representation theory, Lie algebra. Then we want to study the geometry. We solved this equation, but we still don't know the geometry. So, for example, we want to have nice things. One nice thing is, so we want to know whether this is still like we still have a nice vibrations. So that means we still want to know whether it's integrable in the sense of Liouville. Because then we will have this kind of nice vibrations. Okay. But originally, our Theta lattice, it's a phase space has a dimension 2L. L is the rank of the Lie algebra. And we just need to use the Chauvet invariant. That's enough. Okay. But here, our phase space is much bigger. And the Chauvet invariant still they give us Hamiltonians, but that's not enough anymore. So we need to understand that. And so for that, we define the isospectral variety, because we know that when our system evolves like equation 5, then the eigenmatrix of L, it wouldn't change. Okay, so that means like the Chauvet invariant will not change. So we fix that. This is our F lambda. And we take other matrices like L, but with the same Chauvet invariant. Then it turns out that this system is still completely integrable. That means we can find enough integrals to show that. So here there are different groups of people. So DL and T, D is the diet. So in 1986, so they invested for symmetric lattice and actually proposed this method called the chopping method. And EFS is Agnelli, Flaschka, and Singer. And GS is, so they applied this same method to focus on lattice in type A, essentially. And GS is Gehrman-Shapiro. So in 1999, they extended this to all the algebras, semi-simple algebras. So the procedure looks like this, okay? So consider this lattice matrix L and minus lambda IB, so this is the eigenmatrix. And K here means that we throw out the first K rows and the last P columns. So we'll get a polynomial of lambda of degree n minus 2K. And then we take the coefficients. So we have to normalize that because so E0K will not be 1 anymore. So we just for all that. And the other coefficients I, so I, J, JK, this coefficient will be our constant of motion. So they will provide us like invariance of this system. But as you can see, actually, this is the what Professor Restipin will call it like a degenerate integrable system or super integrable system, because for the same system, isomorphic system, there might be different ways to construct the invariance. For example, in Lie algebra, we know that SL4 is isomorphic to SO6. You can use the same chopping method, but you will get a different invariance. And mutually, they don't commute. But each of them will give you enough invariance to say that this is the integrable system. Okay. So that's great. We know their geometry a little bit, and we also know there's also the notion of the tau functions that we defined before. We can mimic everything, except here in general, we can only get the diagonal matrices. It's still the diagonal part is still AJ. We can write it in terms of the tau functions. Okay. Now we want to understand like the geometry more explicitly. What we are looking at here. Okay. So since we see this matrix that the off diagonals are 1, so this matrix is very open. So let me give it a name E. So E is the matrix that has the off diagonal to be 1 and all the other entries to be 0. So there is a theorem of Kostant. It says that for all their matrices looks like L. So for all their matrices in our isospectral variety, there's a transformation. I can always use a lower unipersonal matrix to conjugate it to some normal form. Okay. So there's a space of a dimension L, sublinear space of a dimension L in B minus, such that I can for any element like E plus B minus, I can conjugate it to this normal form. Okay. So so that since we fixed this Chauvet invariance, and the dimension of this isospectral variety is just the dimension, is the same dimension of the neo-potent part. Right. So we make a cook up this map. So this map says, okay, so for each L in isospectral variety, I have a unique lower universal matrix to conjugate to this normal form C lambda. And in type A, C lambda is what? C lambda is companion matrix. So that means for all the matrices that of the form, Hessenberg matrix of the form that I give you, you can find a lower universal matrix and conjugate it to its companion form. So that's something that undergraduates could understand. And then we remember this lower universal matrix that we use to conjugate it to normal form, and that's U. So we have a map from L to U, and U is in this flag is a point in this flag variety. Okay, and it's most of the time it's in the big cell. So now let's look at what we have done. So we have the initial point L naught, and we can do this conjugation process, right? We can find this lower universal matrix that's U naught, and this is a point giving me a point in the flag variety. And as I showed you before, when we solve this linear Toda system on the left, actually we're using U of t conjugated inverse conjugated, and we get L of t. So that means L of t, when I want to conjugate it to the normal form, I need to use U naught times U of t. Okay. But this U naught, we know that U naught is a factor of this exponential TL naught. And the other factor comes from a B plus. I can just pull this factor out, and then I get an exponential TL naught. That's fine, right? But this exponential TL naught, I know that I can use U naught and to get it to the companion matrix C lambda. So I can just exchange this again, conjugate it again. So I will get the final point is exponential TC lambda U naught. Okay. So when you just look at my initial point is U naught, my final point is exponential TC lambda U naught, and C lambda is a constant matrix. Because it's a companion matrix and my spectra doesn't change. It's constant. So this is a linear system, solution of a linear system. Okay. So how do I solve this system? First, I use C lambda to transform my initial condition L naught to U naught. Then I go along a linear system, like that's a linear line, goes through the linear system, and then I use the C lambda inverse to point back. Okay, and then I get my solution. So this is exactly, in this very simple example, this is exactly what people call like inverse scattering method. So we have these 3 steps.
Sorry, what is the choice of U over V?
What?
What's the choice of U over V?
Oh, this is I said before. So for each of this L, you have a unique lower universal matrix conjugated to the normal form. You fix the normal form, then this U is unique. Okay. Especially in type A, it's companion matrix. You can just choose the companion matrix. That will be convenient later. Okay. So now let me address like what I have left. What I left is so in the previous discussion, we'll always assume that I can do this factorization. I can do this factorization in 6, right? But it's not always possible because there are some matrices that you can just not do Gauss factorization. But what's the part that you couldn't do is that sometimes you have to do when your principal minor is not invertible anymore, you have to do some rows and columns like permutation to make your principal minor always invertible. Okay, so that permutation is an element in the while loop. This dot means like I choose a representative of this while loop in this group. So that means so this Toda flow will hit the boundary of this bigger group of cell. And that exactly means, as I said before, so when we couldn't do this, that exactly means the sum of these principal minors, it's not invertible. So it becomes 0. And that's one of these tau k is 0, t star is 0, okay? And that's our singular point. We need to understand that. We need to because other information, for us like study differential equations. Actually, most of the information contains either singularity. So we want to understand that. This is what's called Panway divisor. So how do we do that? We just shift it. We make a shift. So make our origin to be this T star. And we know that so exponential T star L naught, we can do this more general Bernoulli decomposition. U star, W star, B star. And this B star act on a highest weight vector. It doesn't give me a constant. Okay, it doesn't give me anything else. It's just a constant. And the U naught, U star is both of them are lower unit matrix. Of course, I can combine them together. And U naught inverse, I can just conjugate it to the other side. So this is a lower unit matrix. I conjugate it to the other side. It becomes upper, and which upper unit matrix, which doesn't contribute anything. So what I have is something like this. So in line. Then I want to understand what kind of a singularity I will have. Then I have to figure out what's this U and what's this W. So W tells me which Bernoulli cell I hit, and U tells me like how much I can hit. Maybe I couldn't hit like all of them. I can hit only a portion of them. So then there's a problem that I need to find exactly which U and which W star that I can hit. And this is solved by performing like a local analysis. I need to do it locally to find out other, so possible solutions. So I did it in a most stupid way, and most people will just avoid this. But the beauty is it's very direct. You don't need to learn anything. So we want to solve a nonlinear system. What do we do? So I write down. This kind of answers. I don't know whether I will get a solution, but okay, let's suppose like we have a form like this. Okay, we plug it into this into the system, and we find what we need to find. We need to find the exponents, this data k and gamma alpha, data I gamma alpha. We need to find other coefficients a I k b alpha k's. Okay, and I will show you that to do all this, it's possible. And the second one is like when you do this, then you will have some kind of problems. I will show you that you will have some kind of problems called the resonance. And then you need to know. So this resonance is bad because you couldn't iterate your this procedure anymore, and you have to introduce some new parameters. And I will show you that how you find this resonances. And also at last we need to check that. Some kind of compatibility conditions, and also we need to show that these Laurent series are convergent. Okay. So here is the result, and I will give you one example later. So here is the result. First, we need to know what's this data I and the gamma alpha. That's very important because we want to compare coefficients, and we need to know where to begin with. So we need to identify like what's the worst possible singularity that you may have. And it turns out that the worst singularity at the diagonal, it's it's at worst like simple false. It couldn't be worse than that. And actually, this matches with what we saw before, because AIs it can be written as log of tau and then you take derivative. That can at most gives you simple false. Okay. But here we can actually check it like independently with the other method. So the second one is like I need to identify the coefficients, and the leading coefficients is always the most important ones. And when I did a lot of calculations, I find something interesting. So first, other leading coefficients, they are positive integers, and here we have people doing combinatorics, and every time you tell people that you find something that's positive that are positive integers, then you have to know like what they count. Yeah. Otherwise, like it doesn't make sense, right?
Slowly.
And also like the other coincidence is like okay, the number of solutions is exactly the number of elements in the while loop. So a natural thing is you have to combine them together. So here is the solution. So the well group elements will act on this root system and also act on the co-root system. And it matches on the positive co-roots to the negative ones. Okay, so you just look at, you pick any well group elements and you let it act on the co-root system. I will tell you why it's co-root system. I will give you an example why it's co-root system. And then you will map some positive co-roots to negative ones. You just sum all these kind of co-root. And then you expand it in terms of like the simple co-root. And we know that the coefficients has to be positive integers. And it turns out that those positive integers will be the leading coefficients. That's AI0 W because I matched each of the solution with a well group element. So I will denote with W. Okay. So that's the leading coefficient. And then we need to solve like the higher coefficients. So step by step. It turns out that when you solve these higher coefficients, every step you just need to care about this K, AIK, B alpha K. And you throw away all the other terms that you already know on the right. Okay. So this is the linear, this is the linear equation that you have to solve. But here you have to worry about the two things. First, you see that you may have the coefficients KID minus kappa W. So this W here is it depends on the initial equation, the leading coefficients that we saw in the first step. And these coefficients might be degenerate. So it might be degenerate. And those places happens when this K is an integer. When this curly K W has an integer, positive integer eigenvalues. That's very rare. But when it happens, then you will have a problem. You couldn't identify the solutions like uniquely. The other problem is you see on the right, if there's expression on the right is not the linear, is not when your coefficient is degenerate and the vector on the right is not in the linear combination of the columns on the of the left, then you will have a problem. That's a Fredholm condition that you need to put. So you need to guarantee that you can proceed. And it turns out that all the eigenvalues of this KW you can calculate. After you calculate, like you calculate on examples that may not be very complicated, but then you need to match it with some Lie algebra stuff. Otherwise, it's not beautiful. So then at last, I finally identified it with this Lie algebra stuff. We have this topic before, and we know how many eigenvalues we want to calculate. So that's exactly like, some of these eigenvalues, we know that it's a degree of Chablis invariance. And they are exactly like the number of nilpotent elements, that's in that many, or the number of positive roots or negative roots, that many eigenvalues we want to find. And it turns out that I just need to use this W, act on this alpha. And then I take its length. This length may be like positive and negative. What I mean is I just add the coefficients. And then that will give me an integer. That integer is either positive or negative. And if it's positive, then that means I need to introduce some free parameters. And then, so from expression 10, you know exactly, like, then this will give me identification with these free parameters with this Broughot cell, like seems to be so the dimension matches. And also I have enough, I really have enough. So other systems are compatible. I really have enough free parameters here. And also their solutions are convergent. So then we count the number of non-trivial free parameters, and then we know that it's exactly the dimension of your Broughot cell that we had before. So at last, then we can identify this. We can compactify this phase space into flag. Okay. So here is the result. That means like each of the points of the flag variety, I can give you a solution of Toda lattice. And contrary, like you give me a solution of Toda lattice, I can identify points for you in the flag variety. Okay. So this is the one-to-one. Okay. Any questions? Let me show you very quickly a simple example in type B. This is the rank 2. Because in type B, that's the only place that you can see this co-root system. in type other types, you couldn't see curved system, root system, curved system. But curved system is nice. It gives you like an opportunity to connect this with your fancy words like long length dual or something like that. Okay, so I can just write this system like explicitly. We have equation 11. There are six equations, and we know that. So what we should observe is that we know A1 and A2. So then we know B1 and B2. But there are two equations giving me C1. Then I need to make sure that they give me the same C1. And from their fifth equation, I already know D1. But I need to make sure that D1 also satisfies the last equation. Okay. So in any case, if all this works, so that means I just need to know what's A1 and A2. And so as I said, like we have so AIs have at most a simple poles, and then this is the leading coefficients that we need to solve. And you can see that they are nonlinear equations. But you can always also see that you can reduce equation 12 to two nonlinear systems. One of them is degree 2, and the other is degree 4. And you expect the solution, you have 8 solutions. That's exactly the number of wild group element for SO5. And also, so this is how you, I told you that how you get the coefficients from combinatorics. You just let this wild group element act on the curved system, okay? And then, if you have identity, of course, like you map none of these positive roots to negative ones. So that means you get 0. And 0, 0, 0 is always like a solution. And also you have the other 7 solutions. And all of them have positive coefficients. And there are higher coefficients, as I said before, so you can just iteratively calculate it. And the eigenmatrix of this K is you see here, 2 and 4 is always constant there. It doesn't change according to this initial conditions, because that's the degree of the Chalalis invariance. And the other ones, it depends on the initial condition. And if you just list, so we put them like we have 4 unknown ones, and if you just list them in a table, you will find that it's always 1, 1, 2, 3. when I do this calculation, I made some mistake in the middle, but then I realized I saw, okay, 1, 1, 2, 3, 1, 2, 3. Okay, there's one line, it's not. Okay, I have to recalculate it just to make sure. It's 1, 1, 1, 1, 2, 3. Okay, so everything is perfect. You can find at last like other eigenvalues of some huge matrices, and it has a very nice form. And that's the end of this example. Hopefully, I convince you like use this one example to convince you that it's really flag variety. Okay, it's, even in other types, you can do this calculation.
Can I ask a very mean question? Why did you not write this SP4, 4x4 matrix? Why SO5? Why is it better?
Because SO5, I mean, as before, I already calculated. The first example that takes me like months is SL4 because it has too many entries. Like I have to calculate like 16 by 16 and 9 by 9, I think, and then I have to calculate all the eigenvalues. So that's tough, but at last it works. And after that, everything for me is simple. Yeah, as before, I did. So now let me tell you like what's the other story. So you may have already heard like in 1990s, there's a work of Eventhal and Kim. They did something like this. They calculated the quantum cohomology of flag variety, and then it's used two lattice. But there's a mysterious piece here because they use a two lattice, and then they quotient their idea of these Hamiltonians of two lattice, like the quantum ones. But there's a very mysterious piece because they use the three-diagonal two lattice, and their phase dimension of a three-diagonal two lattice is just a 2L. Okay, but the flag variety has a dimension much bigger. So it basically says something very non-trivial. It says like, okay, if you want to understand the quantum cohomology of some variety which has a very high dimension, you just need to understand like something with low dimension. And this low dimension thing is what in 1990 1997, I think like Dale Peterson gave a course in MIT. So he proposed like, okay, this basically build this thing. So that quantum cohomology of flag variety is actually just a coordinate ring of another variety, what we call like Peterson variety. So what the later people call the Peterson variety. Of course, he doesn't call Peterson variety. Okay, so that's something like this.
It's some unpublished paper.
Unpublished. It's unpublished lecture note. It's legendary, like no.
Yeah.
People use 20 years trying to fill in the details, like what he's trying to say. But unfortunately, like he left like a mess after this course somehow. And this Peterson variety is you can define it like this. It's a variety, so it's a closure of something. So it's GE. So this E is a matrix that actually before, and the GE is this centralizer of this element E in G. Okay, and W naught is the longest of all the elements, and B plus that's the identity element in G push B plus. So you just use the DE and push this W naught and then trace other points, and then you take the closure, take out closure in the flag variety. Okay. So if you remember what I told you before, so I told you like for example in type A, so what's this DE? So that's other things that commute with E, right? Other things commute with E. The simplest one is like the powers of E. The powers of E is just a shift. So you have other off-diagonals identical, and then the TIs are arbitrary like constants. That's you take any TI that's in the centralizer of E. So that's exactly if you use this guy SLNE, so push this W naught, that's exactly the solution of three-dimensional lattice. Because like I showed you before, that's what happened, right? So remember this picture that I showed you before. So we have this one. So we have U naught, and we have this guy exponential T C lambda, and push my initial condition, and my initial condition fixed on this W naught, and my C lambda is companion matrix, but this companion matrix I drop this there. So I look at the rational solution. That means like I make all the spectral parameters to be just a zero. I fix the Shaolin invariant, all the Shaolin invariant to be zero. And then I can have T1 here, and I have T2 times C lambda square, T3 times C lambda to the cubic, and then I will get the Toda hierarchy. Okay. And that Toda hierarchy exactly gives me, like the Peterson variety. So, great. I have identified the two things. So first, the three-dimensional Toda lattice is associated with this Peterson variety. That's a variety with dimension 2L. And the
sorry, what type of Hessenberg variety you consider? Semi-simple or regular? Important? Regular.
I will show you. So this N. So yeah, I will show you on next page.
So regularly important.
Yeah. There's only one type. That's
okay. Regularly important. Okay.
Yes, exactly. So I've identified like the solution of a full symmetric full Kostant-Toda lattice with a flag variety, and with three-dimensional Toda lattice with Peterson variety. So there is a whole hierarchy, that a whole set of varieties. That's a Peterson variety is the smallest one, flag variety the biggest one in some sense. So that's called like Hessenberg variety. It's defined in by the following data. First, we have to have an X. X is a map from CM to CM. Okay, we are in type A now. Only talk about like type A. And also you have a height function. H is a height function that's a non-decreasing. That means like hi has to be bigger than or equals to I. And then you can define this Hessenberg variety. It's a subvariety of a flag variety. So when you X by X, it has to lie in the hi. Okay. So here, if we just take this X to be our unipersonal principal unipersonal matrix, like our E. So that's the Yeah, remember it's correct. That's a regular Hessenberg variety. And then I take my edge to be m, so that basically tells me like I put no restriction. And then this will give me like a whole flag variety. But if I take more or less the smallest one, I take a 2, 3, 4, and then m at last, then this Hessenberg variety will just be Peterson variety. Okay. So with that observation, then we want to identify. We want to, of course, we want to identify like these two things. We want to see like in the middle whether we have the same thing. So in general, Hessenberg variety also have another characterization. So the other characterization is actually the one that I want to use. It's in the middle. So Hessenberg variety is like other elements in the flag variety GB plus, such that you use G inverse act on this E, you will fall into this H, and H is some set defined by this Hij, by this Hij. Okay. So here we make a simple observation. If we just take this our companion matrix to be E, that means we set order sublinear to be 0. Then we will see that after the conjugation, you know, other theta C lambda will just commute with E because it's exponential with E. If I just commute with E, and what I left is U not inverse. Sorry, this N is E. This N is E. So U not inverse E U not, and that belongs to H. So that belongs to the same initial point of this H. Okay. So that means like my flow actually stays in the same Hessenberg variety, but I have to restrict the sharply invariant to be 0. And for me, that also makes sense on the differential equation. That means I'm studying the rational solutions of this system. Okay, so the rational solutions, I can just make this identification, and if we use that, then many things we can just, you know, these two theories we can really combine them together. For example, we made this observation like. In the Kostant-Toda lattice, we know this very long that in 1991, Yuancheng and Xie already know that okay, Kostant-Toda lattice it will have its solution will be up. So it will hit some smaller group of cell, but which smaller group of cell, and they identified there are 2 to the L that many, and this is exactly like okay, so you take their other sub-root system, and then you take the longest wild group elements. So generated by their subroot system, and that will give you a group of cell. It will hit exactly those. And these things, only, you know, as far as I know, like it's only observed in Hessenberg variety by like in 2017. So that's you know, they're more than 20 years. And then in type A, actually we can get a little bit more on the Toda lattice side. We can explicitly write down their matrix elements by these tau functions, not just a diagonal, any matrix element. And with that, so if you're working in the group system, you know that actually 15, it's some kind of a bilinear relation. Okay, so all kinds of bilinear relations it has to satisfy. And on the Hessenberg side, I have to connect this like further. So let's generalize like the results of Yuancheng and Xie. So it says like, okay, I want to know how to characterize this kind of Toda lattice that has L band. That means so I have it's not pre-diagonal, it's L diagonal. So how do I characterize like other things like has L diagonal? And we have this following characterization that okay, I forgot to put so this is Yuji and I. So then we just need to understand which kind of group of cells it hits. And here is the characterization. So W star I has to, you know, not equal to W star I plus K for any K bigger than L plus 1 for any K bigger than L. But for that L, we have to have at least 1 that's equal. Okay. And then we know that from the explicit formula, we know that you know, other elements. So below the L diagonal, it's 0. It's 0. So it's a L banded solution. And with that, we can just match this result with the other result from other side of Hessenberg variety. So also in 2017, so actually combinatorists already also identify like what kind of so they want to study like the topology of this Hessenberg varieties. It turns out that somehow we use a different method get arrive at the same solution. So I really think like there's two areas should be like combined together, and they can be very mutually like beneficial. Okay, I will stop here. Thank you.
Further questions?
Maybe I want to say something. This is the so-called the chop approach to the full Kostant-Toda lattice, but very so-called another approach of Xie and our company, and basic statement is we study integral of motion of a full constant lattice for Flach variety. The number of this integral of motion should be equal to number of dimension of Cartesian space and choose 2. Yes, and the question, what is algebra generated by this integral of motion, because this integral of motion have interpretation and there is a polynomial integral of motion and a rational integral of motion, which is also has certain explicit formulas. Yes, and our point is that this dimension is really equal to the dimension of quantum deformation of a Flach variety. And for me, Hessenberg varieties is this particular case of Flach varieties because very certain specialization on the level of Dunkel operators. And okay, and the question is that classical theory of quantum homology gives you dimension or number of quantum parameters is equal to n-1. This is just the number of parameters for the standard classical Kostant lattice. Yes. Do you know the similar number? It is easy to compute the number of parameters for Hessenberg variety, but if it is not Flach variety, or if it is not Peterson variety, it is much bigger than dimensions of classical quantum parameters coming from geometry. Do you know any interpretation of rational integral of motion for full constant lattice as certain standard quantum parameters corresponding to the either Flach varieties or Hessenberg varieties or various many others?
Right, that's something actually I want to do. You see, like in the classical theory, there's there in geometrical quantization. Actually, at least like for solvable groups, that for solvable Lie algebras, that's their theory is relatively complete. And here we're talking about like other coadjoint orbit of Borel. That's a solvable Lie algebra, and we're looking at its coadjoint orbit. I really like to know like how to quantize this. And actually, the first quantum integral system is Kostant-Toda lattice. Like that's studied by Kostant. I really want to, and also that has a lot of connections with with functions. And I really want to know like if we can quantize other symplectic orbits and what kind of interesting functions or theory we can get. But that's a goal. That's still like I still don't have like a concrete result. Yeah.
Well, another question is from my point of view, this is an algebra generated by integral of motion for full constant lattice is isomorphic, not isomorphic, biration equivalent to certain another algebra. This is algebra which defines so-called universal Schubert polynomials. It was defined by Fulton. And there is a natural connection between universal Schubert polynomials and integral of motion of full constant lattice. Do you know some connection of because this connection in some sense not in some sense pure algebraic, that you write some representation of for both algebras and can construct a map, but map is polynomial only in one side. In the opposite side, it will be rational. That means that certain in the images of integral of motion becomes the rational functions. That means it has some poles. Yes. How universal Schubert polynomials will appear in this context?
I don't know yet. Hopefully, yeah. I will definitely ask you more about this.
Yes, and
sorry, may I ask a quick question? So you have Peterson varieties and you have like full flags, but on Hessenberg there are also Springer fibers.
Yeah.
Do you have them appearing like in an actual way here?
There are lots of familiar terms that actually appears here, but the explicit correspondence is still illustrated. For example, like the third-order slice, like universal centralizer. All these things are actually somewhere here in this story.
I see.
Yeah.
Thank you. Very nice talk.
Thank you.
Okay, thank you for talking again.